Hello, my name is Jonathan Nash. I'm Medical Director for the UK and Ireland for a company called Kheiron Medical Technologies that makes artificial intelligence solutions for breast screening. To tell you a bit how I got to this job, I can say that I read my GCSEs, including the STEM subjects biology, chemistry, maths and physics, focused on the knowledge that I wanted to read medicine at university. I took those forward with biology, chemistry and physics A-levels, which normally a 2-year course, although I did have to retake physics before I got the grades to go to Leicester to read medicine. When I was there, I spent 5 years reading my medical degree and an additional year to get another degree. After working for a few years, I then started formal training in radiology, culminating in me becoming a Fellow of the Royal College of Radiologists and entry onto the General Medical Council Specialist Register. From an employment point of view, that looks like this. I was a medical student between the ages of 19 and 25. I worked through all the grades of a junior doctor for the next 10 years, and then I was appointed to become an NHS consultant in Portsmouth, where I worked for 11 years. At 46, I then moved to industry to take on the job I now do. Why is breast screening important? Well, breast cancer is the most common cancer worldwide. We have about 56,000 new diagnoses of breast cancer in the UK each year, and over their lifetimes, about 1 in 7 women will be affected with the disease. Unfortunately, breast cancer kills people. We have about 11,500 deaths in the UK each year from breast cancer, and the 10-year plus survival is around 76%. Early diagnosis with mammography has been proven to save lives, with the NHS BSP reported to save about 1,300 lives a year using mammograms. And just to explain, a mammogram is a specialist breast X-ray. What are the challenges of breast screening? Well, diagnosing breast cancer early is difficult. There may mostly be no signs at all, and subtle signs often overlap with normal features. Unfortunately, if signs are allowed to develop, and maybe the woman develops a lump or some other change in her breast, the cancer is much more likely to be lethal, especially if the woman is younger. Breast screening itself demands a highly specialised workforce. Every mammogram is read by at least 2 readers, and in order to keep their accreditation, each reader has to be reading at least 5,000 mammograms a year. As you've seen from my background, it takes years of training. And in order to get the right balance between them, there are enough readers to get through the work with sufficiently low numbers to make sure everyone has at least 5,000. The service is susceptible to very poor resilience. If you lose someone from that service, it has a big impact on what's left. The nature of breast screening means we have to move women through it very quickly. We screen about 2 million women a year in the UK, and it's important to get them through, partly to make sure we stay on top of the service, but also because we want to give women found to have breast cancer diagnosis as early as possible, and also we want to say to the women who are normal, you're normal, quickly, so they don't have a prolonged period of anxiety. And don't forget, in breast screening, most women are normal, with only about 7 cases in 1,000 turning out to be cancer. So let's talk a bit about what AI is. Why am I showing you a picture of spades? Well, these spades are tools engineered for a specific purpose. If I have a spade, I can dig a hole. I could dig that hole probably with my bare hands, but it would hurt and it would take me a long time. The spade makes it much more straightforward. But what do I do if I want to dig a really big hole? It would take me a long time to do that with a spade. Even if you had lots and lots of people, it would still take a long time to dig a hole like that with a spade. So we engineer different devices for that. We'll have proper diggers, we'll have earth movers, we may use dynamite. And so then a hole like that becomes achievable. It's important to know that while those things help dig a hole like that, if they're designed poorly or if they're used poorly, any of those things can be dangerous. This is a very specialised engineering project, a cross-section through the Channel Tunnel, where we're specifically trying to put in place a tunnel to carry a train under the sea. For that, there were tools specially designed, so the front end cut through the rock, there was a conveyor belt to take the waste away, and as it was going, the tool also lined the shaft it created with concrete plates. And after running for a couple of years, you had a ready-made tunnel. Once you've got that, you can drive your train under the sea. So what is AI? It's a tool engineered for a specific purpose. It's capable of replacing human beings for repeatable or complex tasks, but it is likely to be dangerous at scale if designed or used poorly, and it can be manipulated to malfunction because of its nature. Always remember, AI doesn't understand things like humans do. If I read a mammogram, I'll be thinking, do I need to bring this woman back? I think I can see a cancer in her left breast. An AI won't think like that. An AI will be coming up with an output. Does it need to recall this woman based on its recognition of specific patterns in the pixel data? It doesn't know what a cancer is. It doesn't know what a breast is. So we're simulating human intelligence with machines. And what's become very apparent recently is that there are different sorts of AI. When I'm talking about the products we use, I'm talking about very narrow AI, which is focused on a single question. Its outputs are likely to be predictable and reproducible, and so you can regulate the tools, and they are well suited to healthcare right now. But things like ChatGPT that you'll have heard about in the news are described as generative AI. They have a much broader application, and their outputs are unpredictable and variable because they're not deterministic. So while you see their outputs and you might think, well, that seems plausible, it may not actually be true. That makes them very difficult to regulate, and at the moment at least, they're a poor fit for most healthcare applications. The goals of AI are to include learning, reasoning, and perception, and AI itself includes machine learning and a subset of that, which is deep learning, which makes use of neural networks. So what is a neural network? Well, a neural network is a collection of computer processes working in parallel, working through algorithms that have been trained to the tool. The neural network will look for patterns in the data you feed it, and it may be developed in different ways. So the tools I tend to work with are developed with supervised learning. So we will say, here's the mammogram pixel data, and we will say, we know that this woman was associated with a cancer. You might do it in an unsupervised way, so you might provide it with input data and see what patterns the tool generates for itself. Or you might develop it with reinforcement. So if you think about perhaps a driverless car, you'll set it down a street, and if it runs someone over, you'll tell it that that was a bad thing to do. And if it doesn't run someone over, but stops in time, you'll tell it that that's a good thing to do. So let's talk about the algorithms. Algorithms are around us in healthcare IT and lots of IT all over the place. They are traditional fixed mathematical algorithms that I would associate with traditional computer-aided diagnostics, and we still use for post-processing images to take pixel data and turn it into an image. The algorithms are programmer-defined, so the program will write a code to make a tool do something in a rigid way. They tend to function very much, if this happens, then that should happen. And the coding tends to highlight abnormalities, but that means you don't really have a concept of what normal actually is. One last thing is, traditional algorithms tend to be tailored for a specific configuration. So I have this X-ray machine, and this algorithm will work with that X-ray machine and do this process. Machine learning algorithms are slightly different. So these are what we would use in artificial intelligence computer-aided diagnostics. Rather than being formally coded, the programmer trains these tools, so they're much more dynamic, but how they function is much more obscure. It's very hard to understand how a neural network comes to its output, although the output may be predictable. It would be a bit like taking a slice out of a human brain and saying, well, how did it come to that response? You can't do that. The algorithms can be trained to recognize different patterns, so that might include normal and innocent lesions and, frankly, abnormal lesions like cancers. And they may be enhanced for different configurations and data sets. So you can set up your basic algorithm and then tune it to this configuration, and then if you want to put it in another configuration, maybe a different X-ray machine, you can tune it to that one. But the problem with that is where you've got the dynamism, the tool will be susceptible to learning errors and drift over time as the input data changes. So when we're thinking about AI and breast imaging, our current strategy is not to replace the humans, but to make them better at what they're doing. On the right, we can see a picture here of the current double reading workflow. I mentioned that every mammogram has to be read by 2 readers. So we take the mammograms at the top, 2 readers read it. If they agree, then we tend to do what they agree to do. And if they disagree, we bring in one or several other people to look at the case and make a decision between which of the readers they agree with. In that workflow, there are various opportunities to introduce artificial intelligence. The tools we tend to produce are interested in image interpretation, but there are lots of other opportunities for things like, well, which women actually need screening and how often do they need screening, and how do I manage to make this workflow work a lot better? When I think about interpretation of images, even those outputs differ. So our tools tend to think about, let's make a binary output. Do we need to bring this back? Do we not need to bring this back? Other tools will show a score to indicate the level of suspicion of that image, and some will plot an area of interest or maybe a color heat map over the breast to show where's of interest. Now those different outputs have different applications depending on where they are in the workflow. If you're early up in the workflow, then recall reassure is probably a very strong case. If you want to be near the end of the workflow, where you actually want to have the understanding of what the AI tool was thinking about, then the areas of interest are much more useful, but they'll take more time to interpret. What we're only just seeing in academic circles at the moment is the ability for the AI tools to characterize lesions. That's still not something that's available commercially, and what I mean by that is, oh, I can see an abnormality there. What is it? What is it is a different question. There are lots of companies currently working in AI and breast imaging. Kheiron Medical Technologies is one of the European companies, but you might imagine, you can understand there are companies across the world in this space. What's correct? Now, this is an important thing in breast imaging AI. Most imaging AI thinks about radiographic interpretation, and by that I mean someone looks at the images and makes an opinion, well, I think there's something wrong here, and the AI will be trained according to that output. Breast imaging tends to be different because we've got good access to the pathology data at the end of the workflow. So we tend to say, well, here's a mammogram, and this case was associated with a cancer. So that's very good because we get a good correlation between cancerous mammograms and the end cancer. But the challenge for the humans in the process is that there may not be any human perceptible abnormalities on the mammogram, even though there are pixel data patterns that are associated with cancer, and that's quite a challenge. Now, most of what I do at the moment is taken up with a piece of work that was funded under the NHS, the Accelerating Access Collaborative, and the National Institute for Health Research AI in Health and Care Award. This was announced in 2019 with a £250 million pledge to develop AI systems for healthcare in the UK. There are different tiers of awards depending on how mature the product was. Has it just got regulation? Has it not even got regulation? Does it have an evidence base it needs to be built on? Kheiron won a large award for a 3-year implementation based on its certified product, and the aim was to further develop its evidence base to make it available for broad adoption across the NHS. One of the big problems with that is that at the beginning of the award it wasn't clear what that evidence should look like, and I have to say even 2 years into the award that still isn't certain. So what are we doing? We're doing a number of things under the award. We've got formal studies, and there's a retrospective trial, which means we're taking lots of historic data where we know all the outcomes and running the tool through it to see how its performance compared to the humans in the past. And we'll be taking on follow-up data to see if they disagreed, who was right over time. That's running at 3 centres, up in Gateshead, in London, and down in Exeter, to show a diverse population mix, to show that the tool does work across different subsets of the population and might be applicable to a nationwide screening program like breast screening. We've got a formal prospective study that's starting in Leeds at the moment, That introduces the product into a live screening workflow. We'll be looking particularly there to see, can this even be done? And secondly, how do people behave differently when AI is introduced to their workflow? And we've got a formal service evaluation, which is not quite as worked up as a formal study, a formal trial, but it has been worked up to make sure we can get scientific outputs. From this evaluation, we are calling some additional women back that the computer says we should, and we're looking to synthesize different workflows with the AI tool working alongside the humans. The other thing we're doing is we're trying to get the tool on as many sites in 3 years as possible. We're aiming for about 15 sites, and the reason we're doing that is because with the retrospective study, none of the end users will get to see the tool at all. It's purely a data processing exercise. So we only have 2 other sites that will be seeing the tool in use. And what we want to do is get a much broader exposure. What we've done is developed a sort of silent reading process with the tool working in the background, and we can compare its outputs to the humans on the mammograms as they come in live. It's safe because we're not affecting the screening outcomes. We're reproducing the same thing across all the sites, so we can do some comparisons. And as I say, it gives us much broader exposure and helps us to show that we can adapt to the varied IT and human setups in different services across the country. What are the challenges of the award? Well, 3 years isn't long. And 3 years not only not being long, when you put COVID into it, it's even shorter because you can't get to the hospitals at all. We have had a 6-month extension, and so we should achieve all the things we set out to do. But when you're dealing with a massive potential IT change like that, you've got to bear in mind it's not easy. AI is so new that none of the systems around it exist. So we're having to work with evolving regulatory frameworks, evolving commissioning frameworks, things that people haven't even done yet. We're having to help them develop in order to make our steps forward. Another thing is, just because the Health Secretary says that something is a good idea, doesn't mean to say all of the factions of the NHS are ready to go with that yet. So breast screening, because it affects so many women very quickly, is very tightly controlled, and working with those different opinions is one of the major challenges of this of working in this space. We found that there is no national umbrella for information governance and data sharing relationships and contracting for the tool. So every time we go to a new site, we have to have that same conversation with them and get them comfortable and agree a place where both of us can work together and change and have that, even though we're doing the same thing each place, what those relationships will look like at each site is different. There are other variations across the UK, so what's considered good performance in England isn't necessarily the same in Scotland, Wales or Northern Ireland. And finally, on that point, the Scottish have their own clinical system, the Scottish breast screening system, that works quite differently from the system used by all of the other UK countries, which is the National Breast Screening System. NBSS is 35 years old, so coming along to try and integrate a newly designed AI tool on modern IT infrastructure is itself a big challenge. The aim of the project was to get to the end of 3 years and be able to commercialise straight from the completion of the project. In reality, that's not going to be possible. And a particular challenge when I'm working in a startup company is that we're reliant on an ongoing income. At the moment, we're reliant on a big award and other investment income, but we need to get to a point where we can get revenue income from selling the product. And if we can't go straight to commercialization, that becomes very challenging. So what of the future? So our aims are to secure more funding for more work, building more evidence. We want to work towards large-scale adoption in the UK and abroad. We want to shift over to a robust commercial model with revenue income. We want to ease the pressures on the NHS BSP with a very high quality tool and support better ways of working for the radiologists, the radiographers, and also better screening so it suits the individual women coming through the screening program much better. Fundamentally, the aim of what we're doing is to save more lives. Thank you.